Good morning. My name is Samuel Kusi, and this is Deep Shrestha, and this is Sibia Shrestha. We worked on an ultrasonic positioning system, and this is very similar to a GPS system, except that this is on a very smaller scale, and the role of receivers and transmitters are reversed. In a GPS system, we have several satellites that are transmitting time signals to a receiver, and the position of an object is calculated based on the speed of light. In our system, we have one transmitter sending a signal to several receivers, and the position is calculated based on the speed of sound. Next slide. Yeah, like we explained, we have just one transmitter, we have 3 receivers, and an Arduino controller as the main components of our design. And the next slide. So, the receivers are placed at strategic points of known locations, and we have the transmitter sending signals to these receivers, and the ultrasonic receivers gets amplified through a comparator, and they pass through interrupt pins in the Arduino. And as you see later on, we'll explain the detailed analysis of how the Arduino handles these signals.
The first one wasn't working quite well, so we started with higher gain, but recently we got a new one, which we operated at a gain of 100x, and we basically use a 555 timer to generate 40 kilohertz pulse, and we use Arduino to power the timer so that our clock, we're able to time the pulse sent, and when we receive the pulses at the receivers, and it was easier to calculate. And we're basically on the Arduino, we're high on the 40 kilohertz signal for 0.2 seconds, and it was on low for 100 microseconds. Our T cycle is 0.2%. And the angle of coverage was 60 degrees for each transmitter and receiver. So for our transmitters, we had at least 9 sets of transmitters in the center. We have range of about 15 feet. We just used amplification of 100x and a simple comparator. When we started off using the transmitter, the older receiver, the signal, the gain, the amplification was pretty bad, so we had to use filter in order to take out the noise. But the new one, we only needed amplification and a simple comparator.
All right. After transmitting and receiving the data, we analyzed it through Arduino. For that, we used the algorithm of Trilateration. As you can see, there are 3 receivers positioned at 3 particular locations. The coordinates you see there are in terms of feet. So it's 0, 0, 3, 0 meaning 3 feet on the x-axis, and 0, 3 meaning 3 feet on the y-axis. And similarly, R1, R2, and R3 represent the distances of the transmitter from the 3 receivers. For trilateration, we basically took the time differences, the relative time, to calculate the position of the transmitter. This is the Arduino board. We started off using the Arduino, I cannot say it's 2009, and Italy. And we had to switch to Arduino Mega because it provides more interrupt pins, which are handy for our purposes. The 2009 provides like 2 interrupt pins, and this provides 6. So there was plenty for us. So while doing our project, we went through various difficulties. There were a lot of challenges. One of the main challenges was to be able to determine how much time, the time that the signal took to reach the receiver after it was transmitted from by the transmitter. The next challenge was to provide the pulses, because you cannot simply send 40 kilohertz waves and analyze it to give the position. So we had to come up with a way so that we had pulses going rather than continuous waveforms. And another challenge was there was a lot of noise. So we had to make some filters. We made some low-pass, high-pass, band-pass filters to minimize noise interference as much as possible. And in terms of the applications, you can use it to provide feedback, automation, indoor tracking systems, security. It has many applications in the real world. And now we'll go with the demo. So, as you can see, this is the transmitter, and the 3 receivers are right here. And so that we could cover the entire area, we have a bunch of transducers circling around.